on this very college, this very venue where I did my MSc way back in 85, 87. And some of my friends are also here, batchmates are here. It will be a nice gathering, and it will be a wonderful feeling to be with friends and to recollect all the occasions that we used to have, sitting in the gutters, talking about all college events and other things, the cycling. And there are many, many wonderful feelings. I'm sure every one of you in the future would recollect, will cherish, relish all those moments we all had together sometime or other. It's a wonderful feeling to be back here once again. And maybe I visited maybe 2 or 3 times maximum in the last 30 years or so. Now it's going to be 30 years since I passed out from MCC. So this is a wonderful feeling to be back here on this day. And thank you once again to Sam and also Karunakaran for kindly introducing me to here, this audience. This is the subject which is very close to my heart, geomagnetism, because I belong to Indian Institute of Geomagnetism. So naturally, I would feel that geomagnetism is supposed to be what the subject is close to my heart, and everybody who is working in this area. So I will try to keep it very basic, considering the type of students we have here. I'll introduce you the subject. Geomagnetism is a multidisciplinary subject. It encompasses basic physics, electricity, magnetism, electromagnetism, electromagnetic waves. Then you go deep into the plasma physics, space plasmas. Then you have a little bit of fluid dynamics. Then some geophysics here and there. And finally space physics. So if you see that it's a multidisciplinary subject encompassing from the geophysics to all the way to solar and space related physics. And what we do here in the Institute of Geomagnetism is essentially to study about the geomagnetic field variations. To look at the geomagnetism, it has a variety of spatio-temporal variations, and each one of those periodicities or scale sizes, they will tell you something about what is happening inside the Earth, what is happening in the atmosphere surrounding the Earth, and of course all the way to what is happening on the Sun. So this is a beautiful diagnostic tool which gives you information not only what is happening on the Sun, but also what happens deep inside the Earth, right down to the core. So this is a subject that I would like to introduce you on this occasion. Essentially, so the topics, the origin of Earth's magnetism, that does it originate, little bit of it. Then the magnetized Earth in space, so you have a magnet sitting in space. So how do you handle it? What are the phenomena that this magnet exhibits? So there is a sun there on the other side, and the particles are coming in. Then the cosmic rays are there beyond the sun. They are all coming in. Particles are coming in. Charged particles, energetic particles, KeV to MeV to GeV range of particles. Now, what does this magnet do? How does this magnet see those particles coming in? Will this magnet stop these particles somewhere there? Will they allow them enter inside? Okay. So this is what we'll see. Then finally, some of the fascinating phenomena that we observe, for example, aurora, it occurs at high latitudes. This is the lighting of the atmosphere because of particles coming in. And finally, I will end with space weather, which is a very important branch in these days, considering that there is a number of satellites which are orbiting the Earth, and these satellites, they encounter those charged particles which are coming from the sun. And so the astronauts who try to go out and perform all those experiments in space, they will be exposed to those radiation, particle radiation. And also when you want to set your foot on Mars or Moon or any other planets for that matter, we have to worry about this particular aspect. This is the weather of space. Like the weather here, we talk about the weather in space. Is it important for us? Does it concern us? So we'll study that aspect. We'll just look at that aspect, and then we'll close this session. Okay, magnetism pervades the entire universe. Of course, we all know and we appreciate that aspect. And even looking at the sun, One can see those loops. If we have a UV camera, you can look into the UV radiation, UV filter, you can see that there are loops which are just rising and falling. Essentially, they are all called coronal loops. Essentially, they are magnetic field structures. The hot gas which comes out from the solar corona, they carry the magnetic field along with it, and you can see those hot gas rising and falling, and then the magnetic field associated with it. So, like Earth, Sun is also magnetic. Okay? And of course, the orders of magnitude, if you see, if it is say about 0.4 or 0.5 Gauss here on Earth, there it will be thousands of Gauss on Sun. Sun is very magnetic. Then in 1600, one gentleman was a physician to the royal family, this is William Gilbert. He did a lot of experiments with the magnets, and he used to hammer the magnets, and he used to heat the magnets, iron rods, and then cool them, and then see that as the iron cools, it tries to capture the ambient magnetic field. They try to align the direction of the magnetic field. Initially, when the iron is hot, there is no magnetism, but when the iron cools, then you found that it tries to orient itself along the magnetic field. That is the Earth's magnetic field. So that showed that Earth itself is a giant magnet. So this he proposed in 1600. He wrote a book also on Earth magnet, geomagnet, demagnet, or something like that. This is a very old science. It's even older than when Newton discovered gravity later. But William Gilbert, he found that Earth is a magnet way back in 1600. So this for comparison, the Earth's field is weak. It's a LED finder. So Earth has got a weak magnetic field, and compared to other planets like Jupiter, Saturn, Uranus, and for that matter, Sun, its field is somewhat weak. It's say about 30 to 60 microteslas, or 0.3 to 0.6 Gauss. When you compare it with a bar magnet, its field is about 1 Tesla. So you can see that Earth as a whole, it has a weak magnetic field, but that is enough to sustain life on Earth. Okay. I think this is what I mentioned here. The Earth itself is a magnet, but to the Earth we found it will have the magnetic poles, not full south pole. And if you put the magnetic compass anywhere, it will try to orient itself along the direction of the magnetic field. Of course, it's not only the horizontal direction, but its inclination also. That also will vary. So there are three elements to the magnetic field. You have the horizontal intensity, which will have two components, the north-south component and the east-west component. The east-west component is called the declination. Then finally the vertical component, the Z component. So all these three components vary from place to place, and it was known as early as 16th or 17th or 18th centuries. Then in 18th and 19th centuries, a lot of magnetic surveys were carried out. They tried to imagine how the Earth's magnetic field, how did it look like? What was its configuration like? Is it varying? Of course it is varying from place to place. Of course the direction changes. The north-south, the magnetic declination itself changes. The magnetic north-south is not same as the geographic north-south. So the parameters of the geomagnetic components, they keep varying from place to place. Then they wanted to identify the sources of the geomagnetic field. Where are the sources located? Are they on the sun? Are they deep inside the earth? Are they somewhere in the space or the atmosphere surrounding the earth? Where are these sources located? That was the next question that was asked. After these surveys in 17th century and 18th century were carried out. Then in 1838 or 1839, Gauss is the one person who proposed that Earth's magnetic field has two components. There is one internal component and there is one external component. And then he carried out the observations all over the globe. He compiled the observations. And then he formulated, there was a mathematical formulation he carried out using spherical harmonic expansion. So using this basic magnetism, del cross B is 0. There is no currents there. So we can express B as some gradient of, negative gradient of potential, scalar potential. then we can use del dot B is 0. These are all Maxwell's equations, right? And then we can we will arrive at del square B equal to 0. So this is the Laplace, well-known Laplace equation which we all study in physics, MSc physics. So it can be solved, and then we can get the expression for the V, is the potential. And this, in terms of spherical harmonics and Legendre polynomial, you find that there are two different sources are coming. They try to fit this polynomial to the observed data collected from various locations. Okay. Clearly, there are two sources here. One is the internal source term, and the other one is the external source term. Here, what turned out later on was that there is an atmosphere between two layers. There is one layer here, and then there is another. This is the Earth sitting here, and then there is one region between the atmosphere. So this is the current-free zone, what is called the current-free zone. And then there are two currents which flow. One is JE, which is the external currents which flow in the electrically charged upper atmosphere, upper layers of the atmosphere. And then the Earth, they constitute the internal currents. And so one can, based on the data collected, observations carried out various places, one can use spherical harmonic and one can get an expression for this potential. Now we'll talk about these two sources, the internal sources and the external source. First we'll study about the internal source. As you all know, as you go deeper and deeper into the Earth, the pressure increases, the density increases, the temperature increases. Essentially it is the segregation of matter, no? Based on the mass. The heavier mass settle down deeper and deeper, lighter masses are there at the top. So as you go deeper and deeper and deeper, molecular weight increases, and then finally you go to the core, and then you will end up with iron and some small amounts of nickel. Okay, the iron being electrically conducting medium. So we expect, okay, maybe it's a ferromagnetic substance, we know, and maybe magnetism comes from there, deep inside the Earth, where iron takes over. But it's not as simple as that, because we know the temperature also rises. So initially, you know that the materials, they have got domains, they all get aligned, they all will be aligned in a particular direction. But as temperature rises, they get randomized. And finally, the substance loses its magnetic property. So at very high temperatures, maybe say 1000 degrees or 2000 degrees, 3000 degrees, there is no magnetism there. It just loses the magnetic property. So the core of the Earth is as hot as the surface of the sun, through thousands of degrees Kelvin. Okay. So, and it's all iron there. And again, the pressure increases as you go deeper and deeper inside the core. So ultimately what we end up with, there is a liquid core, it's an outer core. And then as you go deeper, further deeper, the pressure further increases, and finally you end up with a solid core. Highly pressurized, high temperature solid core. And then somewhat lower temperature liquid core. And then you see that there is a gradient in temperature. Very high temperatures, say 6000, 7000 degrees inner core, to say 2000, 3000 degrees outer core, and then further away into the mantle, crust, and all that. So a very steep gradient prevails when you go from the outer core, inner core towards the outer core and towards the mantle. So automatically, you know that we expect convection, right? So if there is a hot gas, if we provide heat from below to a beaker, then you see some kind of a convection taking place, right, in the water, inside the water. So bubbles, hot bubbles grow, they go up, and then they reach the surface, and then it will be replaced by fresh hot bubbles, and then the whole thing will rise and fall. So you will see a large convection type of a thing is taking place there. So wherever you have heat gradients, thermal gradients, temperature gradients, that will be a source of energy for the medium. And that will drive this type of convection. So similarly, deep inside the Earth, as temperature gradient is there, steep gradient, you expect the convection to be very active there. And also, there is a differential rotation. Okay. So inner core and this outer core, there is a differential rotation between these. So what happens is, the whole thing is not rotating like that, but one is rotating fast, other one is lagging behind. So between these two conducting materials, there is a interaction, there is a viscous kind of an interaction between them. There is a dragging between them. And it so happened that when the Earth was formed, there was a small magnetic field. So a very small magnetic field was there initially. it is not as strong as today. There was a strong magnetic field. And that magnetic field was sufficient enough to be sustained by these fluid core motions, convective motions. So you have rotation as well as we have convection there. The mass is rising. No? So this convection and the rotation together was enough to support the small primordial magnetic field that was initiated when the Earth was formed. Unfortunately, Mars also had a small magnetic field like Earth, Mars like a sister planet we call. But the rotation was not so as strong as the Earth. Also, the gradient was not as large as the Earth's case. So Earth is that way it's a very unique planet among the terrestrial planets, among the 3 terrestrial planets. We have Mercury, Venus, Earth, and Mars among the 4 terrestrial planets. Earth had a unique place there. Of course, the giants, extraterrestrial giants we call Jupiter, Uranus, Neptune, they all had very strong magnetic fields. But Earth is very special. Okay. So this is what these pictures tell you. All this. I think I explained it. The computer models of the magnetic field, I think in the early 20th century and later on as the supercomputers started having in the 70s and 80s, the computational tools also evolved considerably. Now, scientists are able to now simulate how the phenomena, how the process takes place there. This is called a dynamo, a geodynamo. Essentially, a dynamo is nothing but you have a conductor across the magnetic field, and then EMFs are generated, right? Basic physics, we have studied that. These EMFs can drive currents. These currents can produce additional magnetic field. And these additional magnetic field, of course, will always, there's a Lenz's law, will always try to oppose the field that is trying to impose on it. Okay. But in the Earth's case, inside the core, what happens is it is not, but it is able to sustain or support the initial magnetic field because of the rotation, convection, and all that. It's a very complicated set of phenomena which is happening there, and the scientific community is now able to simulate what is happening, though they really don't have any idea about what is there deep inside the core. Only through seismic waves and other things, we know that the P waves and S waves, we know that the region there is very high dense material. We know approximately this is the range of temperatures that you have, but nothing beyond that. But using the modern computational tools, the scientific community is able to simulate the geodynamo in the lab. They also have physical experiments to simulate the dynamo mechanism taking place there. And they're able to show this is the type of magnetic field, this is the type of temperatures you should have, this is the type of materials you should have, and this is the type of gradients you should have, and this is the type of motions, convective motions you should have, and you will end up with this type of a magnetic field that you observe on the ground. So we are able to do that now. Now the question is, Mars also had a magnetic field, but as I told you, the dynamo mechanism was not able to sustain. If you see the decay of the magnetic field, it's order of some 10,000, 20,000 years. If we don't sustain it, the magnetic field will decay by about 20,000 to 30,000 years and then stop, no more field. But Earth's case, the field was able to get sustained because of these convective and rotational motions which I explained. Inside the Earth, it's very complicated because I told you there are twisting and rotating motions. So the fields are very complicated there. It is not simple dipole kind of a thing. But when you go outside the Earth, on the surface and beyond the surface, you see a nice dipolar-like feature. The field is coming out here, and the field lines are pointing out inward there. The dipolar structure you see. Now, these are all questions community used to ask. Whether the poles reverse, how frequently the poles will reverse, what will happen to the Earth if the poles reverse. All these questions are being raised. Now we know that the Earth's overall field weakens. Okay, gradually it's weakening. It's not very steep. You don't have to worry now anything about it. But the dipole field is weakening rapidly. That is somewhat of a concern. Because in the past also using rock magnetic studies, people have shown that once the dipole field intensity decreases, then you see the higher order moments, quadrupole, octupole, and those higher order features, they start appearing. And then the dipole gets weakened. But then what happens is after a few thousands of years, it's not going to happen in our lifetime. So we are talking about thousands of years. Few thousands of years, gradually the poles reverse. And many times we have seen the rock, because these rocks, they are the actually tape recorder. They store the magnetic field, the direction and the intensity of the magnetic field at that time. Because once these rocks, as I told you, earlier, if the rocks cool, the magnetic domains inside there, the grains inside there, they try to orient along the direction of the magnetic field. So we know that the rocks melt and they cool different times of the geological history. So whenever a rock cools and goes beyond, its temperature goes beyond the Curie point is temperature below which you can expect once again the reordering of the domains. So every time the rocks cool to the Curie point, you expect the domains or the grains inside to orient itself with the background magnetic field. So when you analyze the rock samples, you will see all types of field directions. And you can trace it where the poles should be. So some rocks show the poles are somewhere here in the middle latitudes in the continental tropical region. Some rocks show that the poles are somewhere else. So the idea of continental drift theory and the seafloor spreading, those ideas got crystallized after after the scientific community started investigating the magnetic properties of those rocks. Okay. So the geomagnetism actually supported ultimately the continental drift theory, the plate tectonics theory, and reaffirmed those ideas. So now coming back to the reversals. Reversals did happen in the past, and the concern now is the dipole field is decreasing. Maybe after 2,000 to 3,000 years, maybe the higher order moments may take over, and then one can see polarity reversal. But it also happened many times in the past that what we call as there is a jerk. That means the dipole intensity decreases rapidly, and then once again it recovers. It doesn't reverse. So such cases are also there in the recorded geological history. So we don't have to worry. Maybe the field will once again recover and once again start decreasing. So do reversals, do they pose any threat to life? Of course, they will have a lot of problems, because as I've been telling you, the magnetism is a perfect shield against all the particles which are coming in, charged particles which are coming in, and mostly from the sun. The sun is near. There are also particles coming from outside the solar system. We call it as galactic cosmic rays. Their energies are much higher than the solar cosmic rays. Solar cosmic rays typically they will be the order of EV to KEV range, whereas the galactic cosmic rays they will be in the range of GeV, because the entire heliosphere, the entire sun and this planetary system, they will have its own magnetic field, and that heliosphere will have a shield against the incoming particles from cosmos. So once that is left over, then the remaining GeV range of particles only will come into the picture. And Earth, again, Earth's magnetism again acts as a shield for those particles. Not only the solar particles, solar ray cosmic rays, but also the galactic cosmic rays. So this magnetism, Earth's magnetism acts as a shield. Suddenly you remove the magnetic field, what will happen? So the entire Earth will be exposed to the particles. And so from starting from the atmosphere onwards, gradually gases will try to escape, and finally the ozone may disappear, and then the particles will gradually enter, and then you will see complete destruction from them. So it's a very the scenario is really fearsome scenario. I don't think it's going to happen next 2,000 years at least. And so we have this magnetic bubble. Okay, this is the entire cushion kind of thing. Wherein inside the Earth is nicely seated there. You can see this is Earth, and then this is called the magnetic bubble. This is called the magnetosphere. I will be using this word again and again, the magnetosphere. Essentially, it is the space surrounding the Earth, where in the Earth's field it tries to order the particle behavior in space. So beyond this is all the sun's influence. Inside this magnetosphere, the Earth's magnetic field controls the particle motions, particle behavior. And now, the shape of the Earth's magnetosphere, if you carefully look at it, this is the sun here, and on the day side, you see that field lines are somewhat contrast inverse. Whereas on this side, this is the day and this is the night. Whereas on the night side, you see the field lines are somewhat stretched kind of a thing. Why does it have this kind of a shape? Okay. So from the sun, we know that the particles are coming in, the charged particles are coming in. So you have the kinetic pressure on the Earth's magnetic field or the magnetosphere. And similarly, from the Earth side, you will have a magnetic pressure applied on the particles. So you see that these two will try to compete with each other. At some place, you will find that these two pressures balance. Okay? And that is the region where the magnetosphere stops there. Whereas on this side, when you come on the anti-sunward side, there is no such interaction because the particles are moving in, charged particles from the sun, they are moving in and they are just sweeping away towards the other side. So when they do that, they carry the Earth's charged magnetic field also along with it. There's very little interaction. But on the day side, these two pressures, they try to oppose each other and they try to balance. So this magnetospheric boundary is formed where the two pressures, they almost balance. This rho v square, magnetic energy, and this is v square by 2 mu is the magnetic pressures, the energy density, and this magnetic density, they try to balance. And there is somewhere about 10 times Re. This boundary is 10 times Re. One Re is about 6,300 kilometers. So you can imagine the distances that are involved there. And that's where the magnetic domain starts from there, on this side, the day side. It's about 10 times Re. As the night side, it goes to 100 Re or maybe 120 Re, 140 Re. And moon is somewhere at around 60 Re. So the magnetic tail of the Earth, it even encompasses the moon, and it goes much beyond the moon to distances of say about 100, 150 to 200 Re. Okay. Now, this magnetosphere, this dynamics is very rich. So whenever you have solar flares or whenever you have mass ejections into the interplanetary medium, and then you see that the magnetic bubble starts vibrating. So because this pressure from the sun will try to push the magnetic field inwards, and then once the disturbance leaves the sun, leaves the Earth, and once again the field will try to relax. So you will see like a rubber band. You stretch it and then you leave it. You stretch it and leave it. Here what happens is you compress the field and then you leave it. Compress the field and leave it. So this compression and the leaving and relaxation, it produces a variety of fascinating phenomena in the Earth's magnetosphere. And they produce radio waves in the VLF frequency. They also produce ULF, ultra low frequency waves, and megahertz frequency waves. So variety of wave phenomena are generated in the magnetosphere because of this. There are also particle acceleration processes which the scientific community is very much interested in. How do particles get accelerated because of this the ringing out of the magnetic field. So a lot of things happen there in the magnetosphere. And very interesting and very exciting to study magnetospheric domain as such. Okay, I think probably I will not spend much time on this because we are starting from the sun. For anything on the Earth, we see what is happening on the sun. That's why the sun's connection is very important. What we do essentially is sun-earth connection. We observe something on the sun through radio telescopes or through some other Hubble telescope or whatever telescopes you have in space, and we have magnetometers on board satellites. So you observe something happening on the sun, okay, and then you try to trace the event from the sun, try to track what is the type of disturbance that propagates from the sun through the interplanetary medium, and how it interacts with the magnetosphere. That is our specialization. And then whether beyond the magnetic bubble, whether these disturbances, whether they can come interior, into the Earth, into the atmosphere, or maybe whether they can reach the Earth's surface, and what conditions these disturbances can reach the Earth's surface. Okay. So these are some of the questions that we try to pose and try to find answers. Probably I will not talk about this. Sunspots are very important. They appear and reappear, they appear, disappear, reappear. And there is a cycle like 11 years periodicity. And every time the sunspots appear and disappear, the sun's magnetic field, overall magnetic field also reverses. Okay. So you will see that the group of sunspots on the northern hemisphere will have one type of polarity, one cycle, and the group of sunspots on the southern hemisphere will have opposite polarity in that same cycle. Now when you come to the next sunspot cycle, the polarity just reverses. Okay. Now the group of sunspots in the northern hemisphere will have opposite polarity, and the southern hemisphere again corresponding polarity. So there is a 22-year cycle corresponding to the 11-year sunspot cycle. We have a 22-year magnetic cycle, magnetic activity cycle on the sun. This is very important when you want to understand the Sun-Earth connection, because the phenomena that we are trying to understand on Earth, they are all connected to what is happening on the sun. Okay. So that's why we are concerned about what is happening on the sun. And some of you might have heard that sun is now undergoing very low sunspot activity, solar activity. Some people are even telling that maybe we are approaching modern minimum kind of a thing. Okay, when the temperatures are going to be extremely low on Earth. Because the magnetic activity of the sun is gradually decreased considerably over the last 2 cycles. So people are saying the sunspots, number of sunspots, normally you see is around 200 to 250, the number of sunspots you see at the peak of the solar activity. So now we are talking about 30, 40 sunspots, that's all. Okay. So sun is also undergoing a decreased activity in recent years, and this is also a concern for us. Because what happens is, as the solar activity decreases, the atmosphere, the upper layers of the atmosphere are going to shrink. Okay. And then when the layers shrink, then the satellites there orbiting the Earth, they are all going to be exposed now to the charged particles from the sun as well as from outside. The sun is very active. You will find like a breathing in, breathing out of the type of thing. So because solar activity provides heat, provides energy to the upper layers of the atmosphere. So they will expand out, they all will breathe out. When the energy is shut off, then they all will contract. So when the atmosphere contracts, then what happens is the satellites get exposed to the particles. The atmosphere is also a shield, in addition to the magnetic field. The atmosphere absorbs the X-rays and the energetic radiation, UV and UV radiation. So like magnetic field, it's a shield against particles. The atmosphere is a shield against the radiation, the UV and X radiation. So when the atmosphere shrinks, then you have those concerns, the satellites directly getting exposed to particles. So it's very important for us to keep a watch on the sun, what is happening on the sun, and how does the magnetic activity behave, and whether the sunspot number, whether it changes over cycles, what will be the next sunspot cycle, how it will look like, how many sunspots we are going to see. So the scientific community is very curious to know. Because we all wanted to know whether the modern minimum type of a thing which happened in 17th century or 18th century, whether it's going to really take place. It's going to be very, very important for us to know. So there are predictive models, there are neural network models which try to address this phenomenon. And taking into account the understanding of the phenomena that we have, they try to pose these questions and try to see. Again, some models are very skeptical. People are very skeptical about some models. Some models, okay, like it won't go so deep. There are again controversies and issues involved in those models as such. So this is the butterfly, very well known butterfly diagram. You see the sunspots appear at about 30 degrees latitude, plus or minus 30 degrees altitude. And then gradually they come closer towards the equator. This is the sun. This is the northern hemisphere, southern hemisphere, and this is the equator, sun. And then when they come closer to the equator, they all disappear. And then suddenly, after a few months, you see fresh sunspots appear on again 30 degrees north, 30 degrees south. And then the whole thing slowly, gradually increases, gradually comes closer and closer to the equator and then disappears. This is the type of sunspot activity that you will see, 11-year sunspot activity. So this is another aspect, solar wind. Of course, in 1958, Parker is one very famous scientist, just narrowly missed a Nobel Prize for that. We have been, community has been recommending his name for the Nobel Prize, but somehow every time he misses an opportunity. He is the one who first said that the sun is so hot that the corona is continuously expanding. Okay. The coronal temperatures are of millions of degrees Kelvin, whereas the photosphere is about 5,000, 6,000 Kelvin. Whereas the corona, the solar atmosphere, is millions of degrees Kelvin, 10 million to 12 million degrees Kelvin. That compare that with this core of the sun, this 20 to 30 million degrees Kelvin. So similar order of temperatures. So solar physicists have been trying very hard to understand what causes this warm corona. Why corona is so hot? Okay. So they are trying to understand. Again, various models have been proposed, and still I think we are yet to reach a resolution. We are yet to understand what are the phenomena, what causes this coronal heating. But Parker in 1958 he proposed that this corona is continuously expanding. So the particles are coming continuously from the sun. Okay, continuously expanding. Because temperature is so hot, no? Temperature is so large. There is a gradient again. So whenever we have a thermal gradient, you will see particles, gases expanding outwards. Okay. So there is a continuous stream of particles, and this stream of particles is called the solar wind. So when you talk about space weather, we would like to know, how does the solar wind look like? Is it fast? Is it slow? Or does it have moderate speeds? Does the solar wind carry a magnetic field? I think next slide I am going to pose the question. Will it have a magnetic field? And if it has a magnetic field, what will its effect on the magnetosphere and the phenomena occurring on the Earth? Okay. But remember that there is a continuous stream of particles which is called the solar wind. And of course the speed varies. If the particles come from the poles, they are very fast. Okay. And they are coming from the equator, they are not as fast. So I am talking about fast speed, slow speed waves. Fast speed waves may be 1000 to 2000 kilometers per second. I am talking about kilometers per second. Slow speed waves, I am talking about 200 to 400 kilometers per second. So the average will be around 400, 450 kilometers per second. That is the average speed of these particles, solar wind particles. These are all coronal mass ejections are very special events which happen on the corona. Suddenly you will find that the energy, again there is a twisting and rotation, like in the Earth's core, Sun has got a differential rotation. The equator rotates faster than the other adjacent regions. So this faster moving equator, now what will happen is the field which is carried by the particles, which is carried by the fluid, it gets twisted, or rotated, twisted and rotated. If so much get twisted, what happens is suddenly one loop-like structure just comes out, along with the hot gas. So we call that as a coronal mass ejection. So it will have a typical magnetic field structure, as well as it will have that very hot gas kind of temperature. So these are called coronal mass ejections. I don't know, there's a movie there. Animation, the UV filter they have used. Suddenly you see these loops. I was telling you this twisting and differential rotation and twisting and all that. So a loop-like structure just gets ejected out, and then they travel towards the Earth. They travel in all directions. These are very, very high energetic events which will have a lot of impact on the Earth's magnetosphere or whatever. Go back. One more sunspot thing also, just show that sunspot thing. Just for any curious young scientist who wants to know what are these sunspots and why do they form, and what is the magnetic field structure associated with these sunspots. These are the magnetic loops, and wherever magnetic field is there, no, actually the fields are like highly conducting kind of thing. So particles can very easily travel along the field lines, but they cannot travel across. So wherever you have field lines coming out, this kind of a loop-like structure coming out, so there is a hot gas that cannot travel in the horizontal direction. Okay, and so the convection tries to equilibrate. Convection tries to bring in some kind of a thermal equilibrium. It tries to bring down the gradients in temperature. Okay. But wherever fields emerge out like that, we find that the convection is somewhat impeded there, those regions, and so so you cannot have heat transfer into those medium, into those regions. So that's why they appear black. They appear black because the temperature is somewhat less than the surrounding regions. Surrounding regions are very hot. They are maybe 1000 degrees or 2000 degrees less than the surrounding. Surrounding is 5000, 6000. These sunspot regions may be 2000, 3000, or maybe 3000, 4000 degrees Kelvin. Yes. Now these are the questions which I asked. What happens when the stream of solar wind interact with the Earth's magnetic field? Okay. And what about the solar magnetic field? The particles coming in solar wind, whether it carries any magnetic field from the sun, whether it has any signatures or imprints of the solar magnetic field. And because in physics, plasma physics, or microhydrodynamics, these particles of the field are frozen together. You can imagine that J equal to sigma E plus E cross B, E plus B cross B. No? You can imagine sigma to be infinity. When sigma is infinity, there is no J. So that means the particle, there is no relative motion between the particles and the magnetic flux. So the particles are frozen into the magnetic field, or the magnetic field fluxes. They are being transported by the particles. So the particles, wherever they are, once they are ejected out from the sun, they carry the magnetic field signatures. They carry the magnetic field imprints along with them. Okay. But they get distorted, they get amplified, they get modified, because you have streams of particles interacting with each other. For example, we have a fast stream trying to overtake the slow stream. And then there could be intermediate streams. What happens every time when the fast stream tries to overtake, the magnetic field between them, it also interacts. And so the magnetic field structures get disturbed or distorted. So now when the solar wind arrives at the magnetosphere, then what happens? So solar wind will carry, as I told you, the solar wind will carry the magnetic field, the sun's magnetic field. That magnetic field we call it as interplanetary magnetic field, not the solar magnetic field. After all, it has gone through all those changes and distortions and all that. We call it as interplanetary magnetic field. So when interplanetary magnetic field reaches the Earth's magnetopath, then there is going to be an interaction. And what is going to happen is what we will see. Okay, other than that, inside the magnetosphere, perhaps in electrodynamics, perhaps we study particle motion. So electron and ion motion in a simple electric field, electron and ion motion in a electron and proton motion in a magnetic field, they guided around the field lines, electric field, they move straight. And then in the combined E and B, they try to undergo drift. And then when you have a magnetic field which has a gradient, there is going to be a gradient drift. And if it has a curvature, of course, Earth's magnetic field has a curvature in it. So there is going to be a curvature drift. So there is a gradient drift, there is a curvature drift, and there is an E cross B drift. Okay. So these are all various types of charged particle motions in electric and magnetic fields, a combination of these. So these are all the different types of. Just for education, you see particles spiraling in the field lines. And then what happens is when they come here, then you have what is called adiabatic invariance. I'm not going to go into that subject. And the particles try to glide along the field lines, and they have some motion along the magnetic field. And they try to reach here into the poles, and they bounce back. So this is called the mirroring motion. Even in lab plasmas also, people try to create this kind of magnetic field geometry. And they try to mirror, because they want to confine the plasma in a chamber. So they apply a magnetic field in such a manner that the particles get confined in that, because of this bouncing motion, mirroring motion. So what happens once the particles are set there, so they get trapped here along this particular field line. Okay. So there are different types of particles of different energies. They get trapped along these field lines. They could just go back and forth along the field and they get trapped there. And some particles, they also may guided around the field lines also. As they enter into the magnetic field, there is a gradient there, and this gradient produces a drift, which will be opposite for the electrons and protons. So electrons will be drifting in one direction, the protons will be drifting in the opposite direction. So they go around and this is spiraling, bouncing, and the drifting from one line to another. So they jump from one line to another, and they try to go along the field line, but once again they will jump. So it's a very complicated set of motions these particles will exhibit. So all these particle motions are observed in the Earth's magnetosphere. These are all various domains of particle environment. So we have the solar wind, and this is the boundary. It's about 10, 12 Earth radii, 16 Earth radii. So this is 12 Earth radii. This This is the boundary. And then you have various regions inside that. These are called the radiation belts. Okay, energetic particles which are trapped there in that region. Van Allen was the one in 1958 who discovered this radiation belt. So it is called the Van Allen radiation belt. And then deep inside you have the upper layers of the atmosphere, what we call as the ionosphere, which is also charged, weakly ionized area. And there's all various domains and the distances are involved there. Yes, now this is what I posed a question earlier. Now if we have a solar wind coming in with a particular direction of the magnetic field, how does it interact? So what happens is, this is, imagine that the solar wind, the sun is here, the solar wind is coming like this, blowing like this, and it had a magnetic field which is directed in the north-south direction, downwards. Now if you imagine the Earth's magnetic field is directed like this, okay, it is just opposite to the bar magnet case. Bar magnet always field lines come out from the north pole and they reach the south pole. But in the case of Earth, field lines always come from the south pole and they end up in the north pole. This conclusion many people have. This is just a notion. This is just a convention which is adopted. The Earth's magnetic field lines come from the south pole, they reach the north pole. Just opposite to the bar magnet case. So here field lines come out from the south pole and they go all the way into the north pole. So here at these locations, subsolar point, where the solar wind directly impinges on the outward boundary of the magnetosphere. So this northward field, we'll see a southward IMF on that side. So when two opposing fields they interact, no? They come closer and closer and closer to each other. No? Ultimately, what happens is these two fields they reconnect. Okay. So this is called a reconnection phenomenon. There are two opposing direction fields. So once they reconnect, then they become one field line. Okay. And then the particles are advecting away. So these reconnected flux tubes, once they are connected like this, the particles are moving like this. Then the whole, once they're reconnected, the entire flux tube goes back towards the right side. Solar wind particles, they keep on advecting them away, keep on moving them away, blowing them away. So every time you have a new field line comes up there, and then solar wind is now coming in, continuously coming in with the southward IMO. There is a reconnection, and then the reconnected flux tube being blown away back towards the right side. So slowly, you find what is called an erosion kind of a thing taking place on the day side of the magnetosphere. Slowly. As erosion takes place, then what happens? Automatically the pressure drops because the part of the flux tube is now being taken backwards behind the Earth. So the pressure drops, the magnetic field pressure drops, and then the solar wind wins, and so the boundary is now pushed slightly inwards. Then the fresh flux tubes they reconnect, taken back, and magnetic pressure drops. Further, the boundary is further inched back towards the Earth. Like this, when you have this coronal mass ejections or extreme events happening on the sun, they can push the magnetic field boundary or the magnetopause boundary from 10 times RE. 10 times RE is the average quiet time distance. They can push it back to 6 or maybe even 4 RE kind of distances. So that means solar wind can come up to that distance, 6 or 4 RE type of distance. 6 RE, remember 6 RE is the distance where the geosynchronous satellites are orbiting, 36,000 kilometers. So once you have an extreme event, and once the magnetopause boundary is pushed to such low distances, 4 RE, 5 RE, then your satellite will be directly, they will be exposed to the particles, charged particles, the solar wind. You can imagine the consequences. So we have been observing such events. Community has recently they have catalogued. There are 4 or 5 such strong events that are taking place wherein the magnetopause boundary was pushed to 4 times or 5 times RE. Fortunately, there was one event in 1989. There was only event in the space era, extreme event. There are no other extreme events we have recorded, fortunately. But once such event occurs, we know the consequences. Okay. Communication systems will fail. All our mobile phones will fail. Okay. Satellites will be destroyed. We will not be able to communicate, not be able to crosstalk, not be able to carry out experiments in space. Astronauts will be exposed. So all kinds of things can happen. So we have to keep a watch on what is happening on the sun. Are there any extreme events taking place there? That's subject of space weather, which I'm going to touch upon now. I think this is just one movie here. Reconnection. These movies you will find in just if you do Google search, you will just land up. You go to the NASA site, you will land up all these very nicely made movies are there, animations. You see, I was talking about the erosion on the day side. These flux tubes are being transported. Once the reconnection takes place there, flux tubes are being transported here. So this is the bubble or the loop which comes out from the sun. There is an ejection out into space. You see, this is the loop which comes out, carrying the magnetic field and the plasmas, the hot plasmas associated with it. Then it will just eject out once it loses the gravity, hold of gravity. Also, twisting is also taking place there. So it just comes out. And then they will be propagating through the interplanetary medium. That's the distance between the sun and the earth. And then they will arrive at Earth. This is the hot gas which comes out. They are traveling now. Okay. You see, so they just hits the day-side magnetosphere. Tremendous force, tremendous pressure. And then there is a magnetic reconnection there. And then the reconnected flux tubes, they are being taken back towards the night side. There is another reconnection on the night side. Then the whole thing, like a rubber band, you are stretching it, and then you are releasing it. It's kind of a thing. So where does the energy go? Okay, the solar, the input energy, whatever it is transferred to the magnetosphere, where does that energy appear? Most of that energy appears in the auroral regions. In the aurora light that we see, most of the energy appears there in the aurora light. There are the blue colors, there are the green colors, there are red colors. So energy comes there in the form of charged particles, and these particles excite atoms and molecules, nitrogen and oxygen gases. And then the de-excitation, and we know in physics all these things. So there is an emission of radiation. And you see those lights. And some of the energy goes into heating up the higher up layers of the atmosphere. Okay. So stored magnetic energy now is transferred to the atmosphere in the form of aurora, in the form of heating, in the form of circulation, convection, additional convection, and so on. A variety of phenomena take place. We'll go back and ask one slide. So just one more slide. We'll discuss about the magnetospheres of other. Go back. Yeah. So as I mentioned earlier, the giant planets, extraterrestrial planets, Jupiter, Uranus, Neptune, they all have very strong magnetic field. The stronger the magnetic field, the greater will be the size of the magnetosphere, the magnetic bubble. So Jupiter's magnetic field is so strong that you can put sun inside the magnetosphere. It's so large. The magnetosphere is so large. You can put easily sun inside. This magnetic field is so large there. And you can imagine the kind of phenomena that will take place on the Jupiter's magnetosphere. NASA has flown some satellites, Jupiter as well as satellites, into Jupiter satellites. They're trying to understand phenomena take place. Next, I think probably the last space weather. So I was talking to you about the weather on the weather in space, because it's very important for not only from the satellites, astronauts point of view, but also for our day-to-day life, communication, navigation, and all that. And when you have extreme events, when you have large electrical currents going up in the atmosphere, they will induce some additional currents inside the atmosphere through induction. So currents flowing in a wire, you have another wire nearby, it will induce currents. You can imagine Earth as a kind of a medium wherein you can see the induced effects. So when you see large electrical currents flowing up in the upper atmosphere, you will see the induced effects on the ground, inside the ground. So suddenly you will find that large currents flow underneath the ground. Then, for example, 1989, I was telling you about the 89 extreme event. So in Canada, for example, all the power lines were all cut off, and transformer grids failed and it burst and all that because of large currents flowing underneath the. So this is called geomagnetically induced currents, GICs. So people are now worried about such extreme events producing the GICs underneath the ground. So not only your mobile phones, suddenly you will find that the whole country is wiped out. There is no power. Okay, and it takes time for you to revive the transformer grids and underlying pipes. They have to be rectified. So we really don't know how many weeks or months it will take to rectify all that. Okay, this is again an extreme scenario. 89, it happened in Quebec. Most of the city of Quebec was cut off by these strong electrical currents, underneath currents. So it's important to study this subject of space weather. Like weather on the Earth, you see what is the weather. I think we discussed all this. particles damaging satellites, the radiation belts I told you, the power grid failure, GICs, this year, the radio communications. So because, of course, now it's not so important because we are directly satellite to receiver communication. Those days we have to depend on the ionosphere. The radio waves will go up, they will get bent, and you receive it at some other place. But now we have direct communication with the satellite. You don't have to worry about it. But those days, this was very important. The concern for astronauts. I think that's the last. This one. I think this one picture, courtesy Bell Labs, they have brought in all the effects. We are going to see when you have extreme solar events or cosmic ray events. Ionosphere currents which will flow there. I didn't touch upon two other aspects. They are there. Atmospheric drag, I told you about the drag. Because once atmosphere shrinks, no, then not only the particles are exposed, but they will also see when the atmosphere expands once again. So the atmospheric drag becomes important when the sun is very active. When the sun is less active, then the particle impact on the satellites are going to be very important. So either way, sun is very active and sun is less active. You are going to see effects on the satellite. The scintillation effect. If there is a irregular structure there, then the satellite, the ground communication is going to get affected by these irregularities or bubbles. They are going to cause deviations in the signal path. Something drastic happens there. Because we all imagine that there is a nice medium vacuum and the electromagnetic wave travels at the speed of light in vacuum, 3 × 10⁸ meters per second. Nice, but it's not like that. There are irregularities there. There are charged particles present there. So they are going to deviate your signal path. So there is going to be an error in your position. The error could be order of 1 or 2 meters. But when you have extreme events, the errors could be much more than that. You also have to worry not only your signal loss, but you may end up producing a large amount of errors in your position measurements. This is another concern. And then when the atmosphere shrinks, then the airline passenger radiation, when extreme events take place. Particles, of course, we don't have to worry at the equator because field lines are closed here. But at the poles, the field lines are open. So the aircraft flying over the polar regions, they have to take a different route. They will not go across, they will not go along the pole, but they will take a different route. They will go around the pole and they will try to reach. So they have to take that into account. Then most important thing is cable disruption. When there are large electrical currents flowing there, then induced currents will flow underneath the ground. So these currents will short circuit your telecommunication cables and they can burst the grids and all that. Okay, so these are the various facets of geomagnetism. Of course, it's a truly multidisciplinary subject. I only touched upon the electrodynamics of the geomagnetism, especially the space geomagnetism. We call that subject as space geomagnetism. I didn't go into the geology or geophysics of the Earth, exactly how does the magnetic field originate and all. It's not our realm of science. We are interested in space physics, we are interested in space weather, we are interested in how extreme events on the sun, how they impact the Earth and the direct impact on society and all kinds of things. Okay. I thank once again Sam and Professor Karunakaran for inviting me here, and I am deeply honored